So, again, it's going to always look real funky like this, but there we go. Look at that. We're doing great. All right, so this will be there. So if I say anything today and you're like, wow, that was really interesting, go back and watch it again or something. But today, I'm going to give an intro on the class, on me, about what to expect, and we're hopefully getting a little bit into the content. So as I mentioned, let's start with the most important part. Me. It's 2054. So who is Dr. Westley James? So I'm an adjunct instructor, so you're the only class I have. You're my one and only. I currently teach high school up at Lake Mary High School. I have a 9-month-old daughter that you can see in various pictures. She's stinking adorable. With parenting comes extra costs, so here I am. It's my wife up there. Her name's Holly. It's the logo for the school I teach at. I've been teaching high school for 3 years. I went to UCF for 9 years. Did my undergrad here, did my PhD here. All of it in physics, though. My PhD, while technically physics, was in physics education research, so how to better teach physics. My research specifically was on how to better design physics courses at the college level to support students with disabilities and subsequently better support all students. So, try to implement some of those practices in class today, hence streaming is one of those things. Other thing I want to point out, small thing, big thing, depends on your perspective. This is the only time I'll ever mention this. I hope it doesn't intimidate you. I hope by the end of the statement that it's a positive thing. But I'm a Christian. I only mention that for a couple of reasons. One is that it's possible to be religious and a scientist. People don't think those two things coincide. But the other thing is that my main role in life is to love and care and support people. That's why I'm a teacher. So I'm a teacher in high school. So I'm a teacher here. And so towards that end, regardless of race, gender, ethnicity, sexual orientation, any of that stuff, all of you have value and worth, and my goal is to support you all. My goal is to serve you all as an instructor, as a person. So please, at any time, anything comes up, reach out to me through email, in person. I'm here to support you. I will do the best I can, and everything I'm doing in this class is towards that end. Teaching is just the vessel I do it in. And again, this is the only time I ever do it. My job here is to teach, not preach, so you're never going to hear me try to proselytize or anything like that, so don't worry about that. So just wanted to mention that because I care about you all. I don't know you yet. I honestly won't get to know most of you. There's 200 and so people in this room, and you really only get to know people through in-person, face-to-face interaction. So hey, if you come get to know me, I'll get to know you as well. Otherwise, you'll be a beautiful face in the crowd, and I'll be a beautiful face on the stage. So I want to get into the syllabus because that is where everything's at. So it's on web courses, and so let's go ahead and jump over to there. So web courses is where everything for our class is. I try anything I present online, anything we do, including the lectures with the live stream, will be posted on eCampus. So all the slides will be posted at least a week in advance. And this includes, so I will be doing, if you notice, there's no whiteboards or blackboards in here. That doesn't really matter for me because any writing I do will actually be on the slides themselves. Hence why I got this fancy laptop where I can write all over the slides and make it, pretty drawings and whatnot. I will post any writing I do, any updated slides online as well. So any of the math I'm doing, any of the concepts, any beautiful pictures I may draw, all of those will also be posted. You can find those kind of in the Files tab. So Files tab's going to have everything. Again, we're going to slowly go through this, but jumping over the syllabus, it's a lot of words. So I'll try to give you the gist of it. My email, wesley.james@ucf.edu. If you email me through web courses, of course, make sure I'm using the right word here. Y'all call it web courses here, right? Yeah. Canvas? Yeah, okay, great. At high school, we call it something else, so I don't want to mix up the two. Whatever. You can either email me through that, or you can email me through web courses. Both go to my email. I will respond within 24 hours. Try and set some healthy work-life boundaries, so don't expect me to respond immediately, because, again, I got a kid that I got to take care of, so I want to spend time with her. But I will get back to you within 24 hours. I can promise you that. Exception maybe on the weekends, because, again, work-life balance is important. So if you email me on the weekends, just heads up. May not respond within 24 hours. But by Monday, I'll get a response to you for sure. Lectures, if you're here, so hopefully you know what time it is, 4:30 to 5:50, Tuesdays, Thursdays. We're going all the way to April, which, hey, is sooner than high school, so get that going for you. CSB 101. My office hours each week are right before this lecture. So they are from 3:30 to 4:15 in Physical Sciences building. If you don't know where that's at, it's right next to the healthcare kind of center. So it's right near that. It's right behind the biology building. 146, so the building is roughly that direction. 146 is on the first floor on the front right corner. So if you are like in the building looking out towards the parking lot, it's front right. If you're looking at the building, the front of it, front left. I'll be sitting in that little room there. Feel free to come by any time for any kind of questions, whether they be life, well, I don't know if there's going to be much life advice. Physics advice I can do way better on. But I'll be in there and I can help you with any problems you're working on or anything like that if you have any questions, comments, concerns. One of the things I tried to do with this course is to make it as low cost as possible. You're already paying a lot of money, so we're using OpenStack's textbook. It's available. I won't necessarily be like going through the textbook, but if you want additional resource, that textbook is available at the beginning of every PowerPoint. I'll give the chapters we're going through. So we'll be going through that. The problems I kind of grab will be from that. 2054 is the second class. It's about physics or about electricity and magnetism. Here's all the topics we're going to be covering. It's a bunch of words. It'll make more sense when we get to them. But really all of it boils down to charges, electric fields, magnetic fields, and circuits. We'll also be getting to light at the end, which I really want to spend some time on. I know a lot of you are health science related. And we have eyeballs, and eyeballs involve optics. So that at least will be very, very relevant. All of this stuff in various capacities will be relevant for you all. Honestly, the biggest learning objective I have for you all is, yes, you got to learn to do stuff like that, but the reason you take a physics class is because no other class, in my opinion, does a better job at teaching critical thinking. The entirety of this class will be identify the unknowns, or identify the givens, identify what you're trying to find the right equation, solve. That problem-solving process applies to everything in life. Think of voting. When you're voting, what do you need to do? You need to figure out what's given, what's valuable to you, what's important, what information exists out there. Then you need to say, hey, what am I actually voting for? What decisions are there? Then you need to process your givens in light of that, what decision you're making. Process it, giving your values, beliefs, etc. That's your equation. And at the end of the day, you come out with who you're voting for. That's critical thinking. That's what you're going to be doing in this class more explicitly than almost any other class. So that way of thinking is done. That's what I learned best in my physics degree, was how to think. So the content I will try to make relevant for you all. I'll try to come up with examples that are health related, since I know that's a lot of you all. One of the first activities we'll get to it, will also be about what your major is, so that'll give me a better context how to situate things in the real world for y'all. Prerequisites, if you're here, you've already got them, so no problem there. Highly recommend that you all meet some people in this class and work together. Because problem solving, you are a human being, I am a human being, you will make mistakes, and so it is very helpful to have other people because you can double check your own work, or you can have someone next to you who's also doing it, and that kind of counts as double checking as well. The more people that are working on the same problem, there's only one right answer. So if you get 3 different answers, 2 of you are wrong. So it's a good way of kind of going through these problems. Highly recommend collaboration. I learned this incredibly useful, especially when I got to grad school. The harder the content, the more you need other people by you. And that kind of applies to anything in life. The harder anything is in life, the more people you need around you to help you through it. So, as I mentioned, web courses, everything's going to be there. We have our lectures. I use the word homework here very conservatively. Let's jump over to actually our eCampus here to see kind of what it's going to look like. So if we go to our grades, not grades, that's going to pretend like that doesn't exist, hide that. If we go to our assignments, there's only 3 homeworks this entire semester, and these assignments can range, your perspective on them can range from busy work to one of the things you actually remember from this class. They're called Physics I Care About, really quick and easy assignments where basically you go through, you take something in the class, and you find some real world example that you care about and explain how the physics we talked about helped you learn how that thing works. Very simple activity. It's worth, let's jump back to our syllabus again. We're going to do a lot of jumping back and forth. The homework there is worth 7% of the grade. Super small amount. Basically, they add a little bit of cushion. Really simple activity. It's when we have a dead week and we don't have a quiz. It's something that's quick and easy, and hopefully you get to apply it yourself, make that real world connection. Clicker question. I sent out an announcement about clickers today. This is the only thing you will have to pay for in this class is a clicker, and I've tried to, again, make it as cost efficient as possible. You can use a physical one, or you can get the online one. If you have a physical one, great. You don't have to spend any money. You're done. If you already have one. If you do the online one, I think it's $15. So that's about as cheap. That's not much cheaper. I can make the course. So no book you need. That's all you need is that clicker. And I do want those because they do help me get a sense of whether you all are understanding it during the class. I'll have random conceptual questions throughout the lectures. you will get most of the points just by answering it, either through the digital clicker you have or the physical one. So easy points there as well. Helps pad out the grade, helps give me some feedback. Nice little thing there. The quizzes are the next big chunk, and I use the word quizzes here. This is my hybridization of kind of quizzes and homework. So if we go again, jump back and forth, you're going to see here on the front a nice little timeline of every assignment and when it's due. It's all laid out. Every week there's going to be a quiz. This quiz will be 5 questions. These 5 questions will be on the topic that was covered the week before. So if you notice here, the first quiz is due Saturday, January 21st, and it won't actually open until this Friday. The rationale behind that is we're going to cover all the content this week. So we're in the week of the 9th through the 13th. So we're going to cover all the content this week. It will open up after we've covered everything, and then you'll have the whole next week to do this quiz. These quizzes are 5 questions. I actually grade them out of 4.5 points, so it's possible to get above 100. And you have 2 attempts on them. You have 2 attempts on each quiz. The questions, so each quiz has 5 questions. They are going to have, if you and someone else take it, you're going to get questions with slightly different numbers. So if you do work with someone, that's fine. Just be warned, you need to have, the process is what matters. You're going to maybe have different numbers, but the process will be the same for both problems. Okay? And when you retake the quiz again, it's going to be the same. The problems are going to look the same, but the numbers will, again, may or may not be different for each one. So after you take the quiz the first time, it's going to tell you what questions you got wrong or right. You're going to be able to look that over and see the ones you got wrong. I want you to spend the time and actually think, all right, how do I figure out how to do those? If you know the process, when you retake the problem with the different numbers in it, you should have no problem getting the right answer. So if you can get the process down, you can get the points, and it should be pretty simple. And the design, the reason I have these quizzes, it's going to connect to the next thing. In my class, I do not explicitly, so like I have those homeworks I mentioned, which aren't really homeworks. I do not have homeworks for you all that are problem solving. I do not have homeworks that are problem solving that are graded, is maybe a better way of putting it. What I instead have, unless we'll jump over to the files again, is I have problem sets. So we're going to have 2 tests in this class, and before each, 2 tests and a final, and before each of those, I have generated a problem set. There's 3 problem sets, so the third one I still need to work on a little bit. If we go ahead and open those problem sets up, let's just pick this one. It is broken into each week's content. And so this is for you all to work on, and these problems, the quizzes will be modified versions of these problems. One of the big things in my class is trying to have alignment between the problems you're practicing, the problems I'm testing you on, quizzing you on, and then ultimately the problems I'm testing you on. So this is kind of your all's go-to for, all right, how do I prepare for the quizzes? How do I prepare for the tests? These problem sets. You can choose not to do any of these problems, and your grade will not explicitly be affected by it. But when you get to the quiz, you may not know what to do. You will say, maybe I haven't seen these problems before. If you do the problem sets, when you get to the quizzes, you will say, some of the problems almost are identical. Some of them are slight modifications, will look a little different, but the process will be the same. And I give the answers to every single problem because ultimately, if you're practicing, I want you to know if you're doing the practice right, if you're getting the right answers. So by the end of this week, you all are going to want, or by the end of next week, before the quiz is done, you're going to want to have worked through all of these problems, 1 through 12, in preparation before you take the quiz. When I taught, so I have not taught 2054 before. I taught 2049 before. That one is for engineers, but it's basically the exact same content. I went through the structure, and when I had a student that said, I'm not doing well in the quizzes, my first question is, have you done the problem sets? And almost 90% of the time they said no. And that would be my recommendation. If you are not doing well in this class, and doing the problem sets is your key. That is the ticket to doing well in this class. Do the problem sets, because I made these, well, I pulled these problems, I chose these specific problems, I make the quizzes, and so I took these problems and I modified them for the quizzes, and I make the tests, and I'm going to modify these problems for the test. So if you've done these problems, you're going to have a good sense of what's going to show up on those 2 things, and you're going to be able to be prepared. I want to make certain you all know exactly what you need to do to succeed, and this is the first step in that process. So back to kind of the grading thing, back to the syllabus. We've talked about the homework, we've talked about the clickers, we've talked about the quizzes. So each week there's a quiz, with the exception of when we, the week after the test, there's not going to be a quiz because just the way the time works out, but that's when the homework will kind of get plugged in. 2 midterm exams. You know what, let's jump way down to the bottom of this. At the end of the syllabus, I have a timeline for what content will be covered during which week. I have the exam days on there. Those are locked in. I can guarantee you that's when we're doing our exams. Whether or not we've covered all the stuff, I'll just slightly modify. I will make certain the exams are on these days so that you know not to plan vacations and whatever not on those. So you can put those in your calendar, locked in. Same with our final exam. That is locked in by UCF. I don't get to choose that, but that one's locked in there. So you can expect the exam to be on this day, first one, second exam on here. Those exams will be worth a decent chunk of your class. I tried to design it so that if you do the math, so our midterms are worth 30, there's 2 of them, 50% each, that's worth 30%. Our final exam is 20%, so half the grade in this class is tests, the other half is everything else. Everything else, if you're working hard, you should be able to get those points, no problem. And then these 2 are kind of your performance, how are you doing on it. The quizzes may seem performance, but remember, after you get 2 attempts on the quizzes, so you'll get to see the exact problems after you've done it once. I mean, the numbers will change, but you can figure out what's wrong and just put that effort in and figure it out. You can even come to me on the week of the quizzes and ask me, hey, I'm struggling on this, and I will help you through them. Again, I call them quizzes, but that's maybe a generous term there. They're more like homework-y quizzes. The last thing is the discussion section. So this is new since I've been at UCF. So when I was at UCF, there was a lab paired with this. That's no longer the case. We have these discussion sections. These discussion sections are going to start next week. You all should already be signed up into one. You kind of had to as part of the class. The way these are going to work is they are basically completion credit. It's an easy 10%. 25% will be showing up to the discussion section. 75%, they're going to give you a couple problems to solve. You get those solved. There'll be a place on eCampus to submit them. You submit them. If you've done them, you get the points. Done. Easy 10%. So that's just additional practice. I will warn you all that, so while my problem sets, my quizzes, and my tests are all very well aligned, the discussion questions, I only found about those recently, and so they may not be as similar as the rest. They'll still be relevant, they'll still be good practice, but because all the instructors, all the 2054 instructors are using the same ones, I don't really have flexibility to modify them to make them maybe match as much. So they may not look exactly the same, but that's all right. It's just completion, and it will still be useful. Practicing any physics problem is still useful. So that's the grade breakdown. The grading scale, it's the classic. Above a 90% is an A, above an 80% is a B, so on and so forth. 70% is a C, above a 60% is a D, F is below that. For the test, I'll mention this real quick. The structure of these is going to be multiple choice with at the end, there will be a choice of, my current plan is 2 free response. You will choose the one that you know how to solve, and that's the one you'll do. If you do both of them, then the instructor, I'll give instructions to the grading TA / me who's also grading them. I'll pick the one that's right. So you can always do both of them. It'll be a time thing, but just heads up on that. If you're worried what the exams are going to look like, they'll be mostly multiple choice with a couple free responses at the end. So missing work policy, there's not really any, the only missing work I could think of. The quizzes are online. You have a whole week to do it. If you somehow do not think you'll be able to get it done in that week, email me, but I try to give a good range on that. The reason I do not want to do it longer than that is because I will start to give out answers and potentially post the solutions, so I can't really run them longer if I post solutions to the quizzes. Again, I want to provide resources for you all to study with. But give me a heads up if you're not going to have internet access for a week, and we'll see what we can do. The test is going to be hard to reschedule, but there is already excused policies in the UCF. And again, I will try to work with you if something outside of this comes up. So definitely 100% any of these medical emergencies, religious holiday, unexpected death, participation in official UCF events, 100% will reschedule. Outside of that, talk to me, and that'll be kind of case by case. We'll figure it out. Cell phone use, just put it on silent. You all are adults in here. I'm going to treat you like adults, whatever. If you want to be on your phone, go on your phone. But just keep it silent. Academic honesty, don't cheat, same old. Course accessibility, this is really important. If any of you are signed up, with Student Accessibility Services, the Disability Office, they're the ones that notify me if you have extra test time or any other accommodations I need to be aware of. Of course, I will include those in the quizzes. The quizzes are timed. They're 30 minutes because I don't want you to have forever to open them up, and just kind of sets a time limit for it, make sure you're prepared for them. The first one will have 40 minutes just to get used to the structure of quizzes. But if you have the extra test time accommodation, that'll automatically be added to that time. So if you have the 1.5 times, it'll automatically be 45 minutes instead of the 30. The tests, I will more than happily get those to you, get them to Student Accessibility Service. Please make use of these. If you are not signed up with Student Accessibility Services, and you identify with any kind of disability that may result in you needing more time or a low distraction environment, please take advantage of this. As I mentioned, part of my research was working with students with disabilities, and I just heard wonderful things about this office and the supports it provides, and just how comfortable they are to talk to and all these things. Reach out to them. It's one of those can't hurt kind of situations to go and talk to them and get extra supports if you may need them. And I fully encourage that, and I'm here to support you as well on that, and all for it. So, safety disclaimer, I reserve the right to make changes. I do not plan, so like I've told you, there's certain things I won't change. I won't change the exam dates because I want you all to know for certain when those will be. But for the most part, 98% of the class should be pretty set from what I've told you. The only things I may change is just small grading tweaks here and there if needs be. I'll be looking at the grades in the class and make changes as necessary. So, anyway, all right. Here's the last little thing. It's when all the breaks are. You probably already know about most of these anyway. Any quick questions about any of this? Yeah.
So, you had sent a message that you're YouTube streaming all of the classes.
Yes.
Will the clickers work if we're doing the class remotely?
It's a great question. If you have the physical ones, 100% no. If you have the digital one, yes. However, there is a slight delay to the live stream. So, if the live stream, maybe you think that maybe I say, 5 more seconds. Well, that 5 seconds in reality may have already passed because there's a few second delay on the stream. That's just streaming, how it works. It's not much of a delay. I also, again, cannot promise that the stream will go off without a hitch. So 100%, yes, if you're at home and you're watching the live stream and all the technology is working and I have the clicker, you should be able to respond on your phone from home or wherever you may be. But that's assuming all the technology is working perfect and all that kind of stuff. So yep, that's an option, not a guarantee. I don't guarantee it'll work because I can't guarantee technology will work. It's too much responsibility to put on myself. But it is an option. Any other questions? Yeah. It's a great question. So for our class, the one thing you do need to bring, some kind of calculator. Scientific calculator, graphing calculator, 4-function calculator. I do not bring a 4-function calculator. I think it's going to be trash. Scientific or graphing is where you're going to want to be. I don't care which. You obviously cannot use your phone as a calculator. You can't use your phone during, classic stuff. You can't use your phone during the exam. That's it. Otherwise, the one thing you'll be able to bring, the way I do it, is instead of giving you all a formula sheet, I let you bring in, and I'll actually provide these for you, and I'll provide them before the exam, a 3x5 note card, where on each exam you'll be able to use one side and write whatever the heck you want on it. I don't care what. I will spend a class period actually showing you what I would put on the note card, and there may be some wiggle room on there just so you know that you have everything you do need. But then you can do whatever you want on that little 3x5 note card. Whatever notes you may want to put, whatever information. If you want to type something up and print it in the smallest font ever and cram that thing full of information, go for it. But that you'll also be able to bring that in. If you don't bring one in, that'll stink. I'll probably still put the equations on the test just because I don't want to penalize you for that. But you will kind of have that little, I don't know if I want to call it cheat sheet, but it's kind of like a cheat sheet. 3x5 note card that you'll be able to bring in as well. That's all you will need on the day exam. You will not, my current plans, and I don't plan on changing it, you will not need to bring any kind of Scantron. If there's a Scantron, I'll provide it. So, any other questions? These are great questions, things I didn't think to say. Yeah? The final, yes. The final will be on everything. That's why it's worth more points, 20% versus the 15%. So exam 1 will be on all the things above here, current, capacitors, electric field, electric force. This one will be kind of, so this is all electric stuff, this is all magnetic stuff, with the exception of circuits, kind of gets bumped in exam 2. And then final 3 will have everything plus optics. So yeah, great question. It will be cumulative. Anything else? Yeah.
What can we expect for like the written response?
So the written response will again be modified. It will be one of the problems in the problem set, one of the longer ones. So, yep, it will look like, so when I say written response, it's just a problem that's got a bunch of steps to it. And the reason I have the written response there is I can get partial credit on those, which is always nice. So currently my plan was 2, with 1 being that I may do a couple more just because there may or may not be partial credit on the multiple choice. I did that before. I'm still debating on that. But I like partial credit stuff because it lets me give you credit for something, whereas multiple choice, it's all or nothing. So it will be one of the problem set problems though that's more lengthy. Any other questions? Yeah.
For each exam, I see you have exam review days.
Mm-hmm.
Should we be doing a separate like exam review sheet, or should we defer back to the practice sets that correlate to the quizzes?
It's a great question. So for the exams, I have a exam review sheet. So during those days, my exam review sheet will mostly be, so I'll be making that postcard then and kind of going through, hey, here's all the equations we talked about. And I may throw out, here's a couple problems that we did with them, make sure you know how to do those, kind of some hints there. So that postcard will kind of be the main thing I'll be working on those, but I may throw in a few problems here and there as well during that time because we will have an hour and 20 minutes. So I'll probably do a little bit of both, mostly working through that thing. Last time I think it took me like 45 minutes to get through since it's all the equations and all the top concepts we talked about. But I will have some time for some problem solving in areas that maybe I saw problems on the quizzes and things like that. I'll highlight those in particular. Yeah. Anything else? These are great questions. All right. Remember, you all can always email me if anything comes to mind, anything you want to ask about. But with that in mind, that's kind of the gist of the content here. Last thing I want to point out, which I already kind of mentioned before, but just to remind you all, the Files tab. So after today, after I do the PowerPoint, you will notice a nice week 1 over here. That week 1 has already the PowerPoint that we're working on. And after today, after I scribble on the PowerPoint some, I'll upload today's PowerPoint in there as well. We won't finish it today because we'll finish it tomorrow since it's week 1, but I will put what we get to today at least on there. So you can look it over if you want to start thinking about things, looking at the problem sets. The other thing I want to point out, and it's going to come up in the PowerPoint in just a second, is that I have this supplemental practice thing here. So I'm going to talk about the slides, but so when you get to those slides, I'll just kind of go through them quickly. Physics is a lot of math. For some of you, that's a good thing. For some of you, that's not a good thing. It is going to be a lot of math. The reason for that is that I told you all critical thinking and I forgot to mention their logic are kind of the name of the game when it comes to physics. Physics is all about understanding how reality works, how the universe works. We don't get to decide how the world works. No one out there got to decide that gravity existed in the sense that they didn't make gravity happen. But what they did do is explain why it exists. And that's all we do as physicists, is explain how the world works to the best of our ability. We're usually pretty decent at it. We make mistakes here and there. It's constantly changing, evolving. We're discovering more things. Quantum mechanics kind of came along and showed us that our current understanding of mechanics wasn't exactly right for small things. Stuff like that comes up. But the reason I mention all this, the world is logical. Many things in the world aren't logical, people especially, but the world is. If I drop this pin, it will always fall. And not only will it always fall, if I can somehow get rid of air tends to make things a little messy because we can't account for all of it, but it's pretty consistent. It's going to basically fall at the same speed every single time, no matter how high I drop it from. That's where logic comes in, cause and effect. And so when it comes to physics, we need math, because the way I like to think about math is the language of logic. So we have English and Spanish and all these languages in the world, and they're used to express complex ideas. I can gesture to a picture, and I can describe it and the emotions, and I need language to be able to express those complex ideas. Well, to explain the logical world, we need a language as well, and that's math. Math is the language of logic. If I have 2 things, and I have 2 more things, and I bring them together, I have 4 things. That's math. 2 plus 2 is always going to equal 4. So we need math to explain the world. We need this language, and math is that language. And so some of you may be very fluent in math. Some of you may not be as fluent in math. And if you are not as fluent as math, I will just straight up tell you this class will be harder for you. That does not mean impossible. It doesn't mean you can't succeed. It doesn't mean you can't get a grade. It just means it will be harder for you. Just like if you went into a classroom where they're speaking Spanish and you do not speak Spanish, or you speak very broken Spanish, you have a hard time, and you'll have to learn the language on top of learning the content. It's the same thing here. So I have provided the supplemental practice thing. It's a bunch of links to Khan Academy. Khan Academy is a great little source. It's got practice problems, things like that, for various areas: trigonometry, vectors, some of the content that was covered before, free body diagrams, conservation of energy, the metric units are here. So if at any point you are struggling, because we are going to be doing problems with vectors, just like we did in Physics 1, we are going to have to know trigonometry for the vectors parts. And so this can be some extra practice if you're stumped. It's a resource that's there. You don't have to use it, but if you are having challenges, again, it's available for you. Wanted to point that out. So let's get over to the PowerPoint and get moving on that. And again, I'm going to repeat myself a little bit here. So we went through the eCampus stuff, or web courses stuff. Talk about it. So one of the skills we need is algebra. Algebra, specifically rearranging equations to solve for unknowns. In this class, we're going to have all sorts of equations. Because again, language of world, language of logic. We're going to have these equations, and sometimes they'll be really nice. Sometimes we'll have an equation where it says x is 3 times 4. And you don't have to do anything fancy. You just multiply and you're done. Other times you're going to have equations where the thing you're solving for is all stuck with a bunch of stuff next to it. It's stuck in the equation. And so algebra is basically the opposite order of operations, and you are going to have to be able to do it. It's going to come up. And so things I tell my students in high school, because I teach physics there as well, if you can do the order of operations, algebra is just all about doing the opposite. You look at this, and instead of doing the order of operations, which is parentheses first, you start at the bottom, you say, is there addition, subtraction? Oh, yeah, there is. All right, do the opposite of that. Subtract it over. All right, what's left over? Oh, I've got some multiplication. That's the next ladder, because we work from the bottom up. I'm not going to go through the whole math order of operations for this. When we solve problems, I will try to do as careful as possible and show you the steps I'm taking, but that is going to come up. Next, we got trigonometry. You need to know that if I give you an angle, and I give you a vector, and I say this is another vector, how to break that into x and y components. So when I'm talking about vectors here, and trigonometry and vectors kind of go together, we are going to have vectors. Vectors is an amount with a direction, which is very important, because if you just have an amount, you're not going to really get very far. You need to be able to take, let's just say this one is, I'm been doing this a lot where I make up random problems on the fly and draw them. That's why I mentioned to you I'm going to upload this stuff. So let's just make up a random vector. Let's say it's a force vector, because it's physics and we talk about force. So we have a force vector pointed 30 newtons. Who knows what's doing it? Maybe someone is pushing something. Let's say the angle here is 10 degrees. In math problems, we have to be able to break that into x and y, because, and we're going to see a problem at the very end of this, we're going to have to do that. We have to break things into x and y to add them. So you know what? Let's do that hypothetical problem. Let's say we have one 30 newtons this way, and we have another that's 20 newtons this way. This one's, 30 degrees. Doesn't really matter. To add these vectors, you don't just add 20 plus 30 and call it a day. It's not how it works. You have to break it into x and y components. And remember, to get x components, you make a beautiful, in all these cases, you make a beautiful triangle. Trigonometry is all about triangles. Let's make this arrow a bit bigger so I don't have to write super tiny. So there you go. We have an x, we have an y. X is horizontal, y is vertical. So this x component for the first one is going to be 30 times cosine of 10. And then we're going to add that to this one, which is going to be 20 times cosine of 30. But we have to remember also that to the right is positive, to the left is negative. I'm just going through this problem to remind you all, you've done problems like this in Physics 1. If you have not, then that's not great, but hopefully you've seen this before. Hopefully it's looking familiar. I'm just working through this just to remind you what these problems look like, because we are going to see them in this class. Next one, sine gives you the y component. And then the other one, 20 times sine. This one's up and down, so we get to keep it positive. And great, you get the x component, you get the y component, and then we use our classic Pythagorean's theorem to get them back together. Very quick, because I expect that you all have seen this before. I will not go this quick on problems that we're solving in class where it's new stuff, but just wanted to run through a quick thing to remind you what the heck I'm talking about when I say vectors and trig. We are going to be doing that. You are going to have to be decent at it. There will be a problem with the first quiz that involves it. So, all right, vectors and scalars. You need to remember the difference between them. Vectors are really important, so I told you they're important. We did some math on it, but why? Because if you want to get to Tallahassee, you better be traveling north. It's not good enough to be traveling 30 meters per second or however fast you may be going on the highway. If you're going south, you'll never get to Tallahassee. So, directions matter. You know that if you've ever driven anywhere. You got to be going the right way, so we have to, the direction you're traveling makes it, we have to make that explicit in problems. We have to talk about that because it affects things. Gravity is down. It's important that we know it's down because it makes a big difference if gravity's up or down. So, vectors are really important. We have to go through that extra complication because we live in a three-dimensional world and it makes that impact if you have the wrong direction. And we have to add our units. I have a little penny jar in my classroom, in my physics class, and every time I say don't forget your units, I put a penny in it, and then I only had to do that for about a semester, and then they had it down. I am going to say it a lot in this class. Don't forget your units. The classic example that I give my students in high school is I say, if I asked you to mow my lawn and I told you I'd pay you $50, would you agree? Well, some of you may say yes, because you may make the assumption that I'm talking about $50. It could be 50 anything. 50 blades of grass, 50 cats, 50 dogs, 50 high fives. If you do not put a unit, your number means absolutely nothing. If I told you I had 3, you would say 3 what? That's what I will ask you if you give me an answer without a unit. The unit is necessary to define what the heck you're talking about, to make the number mean something. This isn't a math class, it's a physics class, which means we're talking about the real world, which means our numbers actually mean something, for good or for bad. Add some extra complication, but hey, at least it's real stuff. So there's an example. It can be X, Y, Z, but we need our units. So there you go, all caps, exclamation point. All the units you plug in your problem must be base units. This is something, again, you saw in Physics 1. This is all stuff you've seen before. This may be meters, kilograms, seconds. See, rule of thumb, your unit should only be 1 letter. The only exception to that is kilograms, and I don't know why that is. There's some history behind why they didn't choose to use gram as the base unit, but here we are. You want whatever you plug in the problem. I am going to give you all sorts of weird units, hence this crazy table here. Charges are small. We're going to learn the protons and electrons, and they are itty-bitty. So we're going to be seeing, for example, we're going to learn about coulombs in a second. That's what that C is. Coulombs, nanocoulombs. We're going to be working with nanocoulombs a lot. If we look at our handy-dandy table here, that means whatever number I have, when I plug it into the equation, I better multiply it by 10 to the minus 9 before I hit enter. If I put in my problem, say I give you 3 nanocoulombs, and you just put 3 in the problem, it'll be wrong. You're going to have to convert that to coulombs, which would be 3. Show you all this real quick. Better 3 times 10 to the minus 9 coulombs. This is also a good time for me to show you all. I will not be writing times 10. I will at first just to get used to it. Scientific notation. That is a couple extra letters that I want to write. So whenever you all see me write times 10 to the whatever in this class, whether it's positive or negative, it's going to look like this instead. 3e minus 9. It's a little shorthand. And the reason I like to write it this way is twofold. One, it saves me work. I write 2 less letters than this one. This is x1, this is 3, this is only 1. Saves me a couple times. It's a little shorter, it's a little more compact, but also it's very practical because in your calculator, a lot of your calculators will use a capital E instead of a times 10 to the. So this will also help when you're writing your problems to make certain what you plug in your calculator looks like what you have written down. So it's a little handy thing there, but that's how I'm going to write my times 10s. It's that E. I will repeat that a few times so that we're all good with that notation and not surprised and not super confused. So things have to be in base units. And to get in base units, you need to kind of remember this. This will be a thing when we get to test. It will be something I will add to the note card. I will take some of the most common ones, nano, milli. That's really the only micro. Oh yeah, that one's popular because it's real small. Nano, micro, milli, those are going to be classics that we're going to be using. So that's something I'll even put on the note card because if you don't need to memorize it, don't. All right, let's actually get into things. So today, we're going to be talking about electric charges and forces. Physics is all about the fundamentals. Engineering is applied physics, and so engineers, they take physics, and then they skip a bunch of content and actually start applying it in the graduate classes, and they miss a whole lot of things there. Physics is where you're going to start literally from the foundation of reality. You all learned last time about, in your first course, about forces and mass and energy and things like that, and gravity. This class we're going to look about one of the two. So there's 4 fundamental forces in the universe: the gravitational force, the electromagnetic force, the strong force, and the weak force. Gravitational force is pretty straightforward. 2 things with mass experience a gravitational force and pull towards each other. The electromagnetic force is a little more complicated. It involves electric fields and magnetic fields. It involves both of them. Turns out that they're one and the same, depending on how you look at it. It's kind of a huge hand waving over a lot of information there, but electric fields and magnetic fields are, you can transfer between them. We're not going to learn how to do that in this class, but it's possible. Fun facts: the stuff we're going to be covering in this class is responsible for more things that you've experienced in your life than gravity. Gravity, the only thing it really does for you is hold you to the ground. I mean, it holds everything to the ground, which is, pretty nice in the planet's orbit and stuff like that. The electromagnetic force is responsible for every single thing that's touching. Every single interaction in your body is governed by the electromagnetic force. Every interaction between every particle, with exception of gravity and planets holding together, is electromagnetic force. We're going to learn that the reason when you touch something that your finger doesn't go through it is because of the electromagnetic force. The reason that you can see there's electromagnetic waves. The transfer of ions across cell walls, electromagnetic force involved. MRIs, like so many different things. We utilize this all the time. Your phones are picking up electromagnetic waves of all sorts. Visible, well, not visible really. Invisible ones that are passing through your body all the time. Electromagnetic force. It is everywhere. Literally, it's everywhere. Like the electric fields are all over the place. So we're going to learn what the heck they are, where they show up, how to calculate them, what things are affected by them. And so today we're going to kind of cover the fundamentals there. So let's get started. We're not going to experiment with charge. So real quick, chemistry overview. The model of the atom isn't what we always thought it was. We started with this plum-pudding model. It was, you got your protons, electrons there. Then we get this idea of the nucleus. And I don't think I have the crazy picture anymore, but nowadays it's even more confusing, where we have this electron cloud and we don't actually know where electrons are. There's a probability, interquantum mechanics, all that jazz. But what I wanted to mention there is that atoms, so this is kind of the first important thing that we're talking about today content-wise. Atoms are made of protons and electrons. These are the fundamental particles that have charge. Everything in the universe is made of protons, neutrons, and electrons. We're going to see in the slide in a second that neutrons are neutral, protons are positive, electrons are negative. And so protons and electrons get this magical thing called charge. We give it the unit of Coulomb, named after a guy whose last name was Coulomb. You could discover something, you get a unit named after you. So something to look forward to in life. Good luck. Newtons, Coulombs, Amperes, all these things named after people. So reminding you all, the unit is what's going to go after your answer. So I say a problem, and I say, hey, find how much charge there is. All right, you find it's 30, we're going to say nanocoulombs. The reason I didn't put coulombs here is because it turns out that 1 coulomb is a heck of a lot. I did a problem today, actually, with my class where we had 1 coulomb, about 1 coulomb 5 kilometers apart. And the force that those 2 coulombs experience, the 1 coulomb and the 1 coulomb experienced 5,000 meters apart, was about 30 pounds of force. Even though they're 5 kilometers apart. That's how much 1 coulomb is. That's how strong this force is. Way stronger than gravity. The variable, meaning the thing that's going to show up in the equation, so the unit's what goes after the coulomb, goes after our number. Now I'll get rid of the nano just not to confuse people, but 30 coulombs, which is an insane amount of charge, but it gets the idea across, it goes after the number. The variable is what's going to come up in the equations. Little q if you only have 1 charge, big Q if you have a lot of them. So point charges literally just means you have a charge that's tiny, tiny, tiny at a single point. Net charge means add all the little point charges together and you get capital Q. So, what is charge? Well, it's a property of matter. Sounds real archaic, which results in the matter experiencing a force in the electromagnetic field. Sounds real weird, but here's what it comes down to. What's mass? Mass is the quality of something such that it gets affected by gravity. Things with mass get affected by gravity. We're going to ignore light for now. Yes, it gets affected by gravity, but that's all weird. Mass, how do we know something has mass? It gets affected by gravity. How do we know something has charge? It gets affected by electromagnetic fields. What is charge? That's a great question. No idea. But things happen. What's mass? I don't know. It's things, again, the best I can tell you is it's things that get affected by gravity. Why do things have mass? I don't know. I didn't decide that. They just do. Why do things have charge? Because they do. Why do protons have charge? I don't know. They do. We just measured it. They do. Why do electrons have charge? They do. That's as much as I can tell you. If we wanted to go a little bit step further, we could say, oh, protons are made of quarks, and quarks have charge. But then you're in the same exact situation. Why do quarks have charge? I don't know. Ultimately, physics always gets down to that. If you keep asking why, eventually you just get to a point where it's like, because that's the way the world works. Ultimately, all of physics is an observation of reality. Why is reality the way it is? Insert religion, philosophy, etc. Physics can't answer those questions. All right, so as I mentioned, here's our beautifully confusing picture of the new atom. You got your proton here, which is itty bitty. It's not even scale. That dot should be even smaller. If we made it small enough, you wouldn't see it. You got your nucleus in the middle, made of protons and neutrons, and you have your electrons. I highlighted these because these are important, and they're going to show up in equations, specifically the charge. How much charge do they have? Very little. They're a proton. They're an electron. They should have very little. They're itty bitty. Their mass is also itty bitty, 1.67 times 10 to the minus 27. And just to get us used to the notation I mentioned before, if I want, I could rewrite this as 1.67 e to the minus 27 kilograms. Same thing. Just want to remind you all, I can write these things with this e instead of the times 10. The more I show you it, the more comfortable we get. But the charge, protons are positive, 1.6 times 10 to the minus 19. Electrons, it's the exact same number with a negative side in front. So if I have one proton, I have a charge of 1.6 times 10 to the minus 19. If I have two protons, multiply that by 2. If I have three protons, multiply it by 3. If I have an equal number of protons and electrons, they cancel out. They don't literally explode, nothing like that. But the charge cancels out. You could just kind of add it up. So if I have one proton, I have positive 1.6 times 10 to the minus 19. If I have one electron, I have negative 1.6. And if you add those two numbers, you have zero charge. Most things are neutral. Atoms in general are neutral, though they don't have to be. You can ionize atoms, but let's imagine they're not ionized and they have, that was one of the things you learned in chemistry. The number of protons is the same as the number of electrons. So if you have 30 protons, you have 30 electrons, the charges end up canceling out. Now, if you happen to rip away some electrons or shove some extra electrons in there, that story changes. At which point we'll see what that looks like and how to calculate that. It's super simple. Again, we're starting from the basics here. But you do need to know the charge of a proton, charge of an electron. Do you need to have it memorized? Not if you write it on your note card for the test, which I probably will, because I forget this thing. If I didn't teach this topic for a couple years, I'd forget this number. It's a number. Why would I remember it? I will never have you all memorize constants. There will be some way for you to access them. I will never have you memorize equations. There will be some way for you to access them, but you will need to know how to apply them. So, all right. So charge is quantized. This is where the word quantum comes from. All quantized means is that it's set numbers. You can't have half a proton. You can't have half an electron. Doesn't exist. If you try to break a proton in half, I guess technically it turns into quarks and weird stuff. Let's pretend quarks don't exist for this class. But let's imagine that you can't break it in half. Technically you can, welcome to most things in life. There's always a technicality. But in general, you can't break a proton and an electron in half. And so every charge, no matter what in the universe I have, if I meant to bring a balloon, sad I didn't, but if I had brought it and I rubbed it against my hair, it would have a set amount of charge on it that would be some multiple of 1.6 times 10 to the minus 19. Everything that has charge, if it doesn't have zero charge, it'll be some multiple of 1.6 times 10 to the minus 19. Because that means it either has extra protons or extra electrons. It's going to have one of those two. So it's going to be some multiple. This equation looks real fancy. You know what I realized here? I used the wrong Q, so shame on me. Let's change that to a capital Q. Because remember we said net charge was a capital Q. There we go. Oh, that's a W. There we go. Now we're happy. Capital Q, the net charge, is take the number of protons, subtract the number of electrons. This E, just to remind you all, is that 1.6 times 10 to the minus 19. 1.6 E minus 19 coulombs. And literally all this equation is saying they cancel out. If I have 8 protons and I have 5 electrons, well, 5 of those electrons will cancel out 5 of the protons, so that's subtraction. 8 minus 5 is 3. And then I do 3 times 1.6, and that's my net charge. I have 3 extra protons. If I have 3 extra protons, well, I need to multiply that by the charge per proton. 1.6 times 10 minus 19. There, I got my net charge. Done. Now, the reality is it's really hard to get 5 protons and 3 electrons, but we'll keep the number simple for now, just for the idea of the concept. Charge is a conserved quantity. You cannot destroy protons. You cannot destroy electrons. You can transfer them, though. So anytime we talk about charge, we don't make them out of nothing. We don't pull them out of thin air. We can't do that. We don't have that power. I don't know if it'd be great or not. Maybe it would be. There'd probably be some consequence. But it just, remember, mass cannot be created or destroyed. Well, these things have mass, so you can't just poop them out of nothing. You got to pull them from other things. So if I, imagine I had my balloon that I meant to bring. If I rub that on my hair, it is stealing electrons from my hair. It becomes charged by stealing electrons from my hair. And my hair is technically charged the other amount. So if the balloon is 1 coulomb, well, my hair's got to be negative 1 coulomb now. It's got to be the opposite. Neutral does not mean no charge. Almost everything in this room is roughly neutral. It does not mean that everything in this room is not made of protons and electrons. This table has protons and electrons. My calculator has protons and electrons. I have protons and electrons. I forgot about that there. So you still have charge. You just don't have extra. You don't have extra protons, or you don't have extra electrons. They all cancel out roughly. All right. So now we're going to see our first clicker question. I do air quotes because I unfortunately don't have the clicker base. I'll have it for next class. Forgot to mention this. Clicker questions won't be officially a part of your grade till next week. I'm going to go ahead and say Thursday is the first day they'll be a part of the grade. Give you all time to make certain they work. On Thursday and Tuesday, so I'll start actually doing the clicker questions, letting you all respond to them, and I will post those grades not as an actual part of your grade, but just to make certain that yours is working. So on Thursday and Tuesday, I'll post grades for clickers, which won't actually be part of your grade. It'll just be so you can see whether or not yours came in or not, whether yours is connected or not. Give you some peace of mind moving forward. It'd be a real shame if you got halfway through the quarter thinking you were answering questions and it wasn't actually registered. All right. So here's my hypothetical clicker question, which normally I'd run and I'd say, you have a minute to answer this. The timer would go and all that kind of jazz. But still try it. If I have 7 protons and 3 electrons, what's the net charge? It's a math problem, but pretty simple one. Try it out. I'm still going to give you 30 seconds, 45 seconds, something like that, a minute. Try out this problem. See if you can get the right answer. See if you can apply that idea of charges canceling out, apply that idea of the equation. And this will also be a great opportunity for me to show you all the beautiful 4-step problem-solving process. Another benefit to having a friend nearby, a friend in the class with you, someone you get to meet and greet. Highly recommend by this class. Get to know the people around you. People tend to sit in the same spot every class, so, at the end of class, if the people don't run away from you, get to know them. Say, hey, my name's this. We're in the same class. What's your name? Blah, blah, blah. Because when you sit together and do these clicker questions, you can check if you got the same answer. It could be a nice little handy way of checking your work. If you got different answers, one of you is right, one of you is wrong. Or you're both wrong. You just both can't be right. All right, so let's start working through this problem. See how we do. So, I'm going to show you all the 4-step problem-solving process. It's a little overkill for this problem, but it'll get you used to this process. Whenever you are solving the problems on my problem sets, you can use this recipe to solve them. I already mentioned it previously. There's technically step 0, which doesn't apply to every problem. That's why it's not always going to show up. Step 0 is draw a picture of the problem. So you know what? Why not? Step 0, let's draw some protons. 1, 2, 3, 4, 5, 6, 7. You don't need to do this for this problem, but it is a nice little illustrative device. And then I have 3 electrons. It's going to be very useful to draw pictures for certain problems, especially where vectors are involved. You definitely want to draw a picture when vectors are involved, and I will be doing that as well because it's just so much easier. Keep tracks of all the information. The more you write down, the less you have to store in the head, the less your brain has to work, the easier life is. So, I have my 7 protons and my 3 electrons. So here's my, again, overkill problem solving. First step, identify the givens. Well, I have 7 protons and I have 3 electrons. Again, this is going to look overkill. You're going to be like, this is stupid. Why is he writing all this down? I want you all just to see this process. It's a good opportunity to show you all, because when we get to more complicated problems, I'm going to be using this, and it is a great technique for solving problems. If you are ever stumped on a problem, you don't even know how to begin, start with this process. Identify the givens. Identify the unknowns. What are we solving for? Net charge. It says, what is the net charge? So we can jot that down. This process can get you moving when you feel stumped. Again, when I work with my students in high school, when I go around and they say they don't know what to do and their paper's blank, I say, let's start this process. What's given? What's unknown? Applies to anyone at every stage. All right, step 3. What's our equation? Well, there's only one of them, thankfully. That's going to increase as time goes on. But Q net equals number of protons minus number of electrons times that 1.6 times 10 to the minus 19. And before we even begin this problem, the step 4 is plug and chug. What do I have extra? Protons or electrons? Protons. So should my final answer be positive or negative? Great. There you go. That's good little thinking there. Use techniques like that. I'll try to mention from time to time, because I could have given you this problem where half of them are negative, and you know those aren't the right answer. You can eliminate some problems real nice that way. So we know it's going to be positive. All of them are already positive. So we plug and chug. Q net equals, 7 minus 3. Again, very simple problem. If it seems real stupid and you're wondering why Dr. Jane is spending so much time on this, again, just to get you used to the process, I will tend to show more steps than less in the off chance that you are stumped. Times 10 to the minus 19, and this is actually a great opportunity to practice plugging scientific notation in your calculator. At this point, I assume you all have a calculator. If not, make certain you have one. Your calculator, you want to know how your calculator works. This is my calculator from high school. I still have it to this day, 12 years later. There you go, you can age me now. 4 times 1.6, and, did I actually give you all that 0.08? I didn't. So you may be wondering, what the heck? Why is that 0.8 there? Let me erase that for the sake of make your all's life a little easier. Technically, the charge of a proton, the charge of an electron, it's got a few more decimal places, but I didn't give them to you all. So 1.4 times 1.6 is going to come out to that 6.4 times 10 to the minus 19. And then here is the last thing that you need to be careful of. We got a bunch of C's, we got a bunch of Q's. This is where you have to remember which is the unit and which is the variable. Coulombs is the unit. That needs to go at the end. Q is the variable. That's what goes in the equation. That's going to be a classic thing that'll mix people up. I will purposely put that stuff in there to make certain you know which is which. So I will have problems in the quiz and stuff where it will be the wrong. I'll put the unit, I'll put the variable, put the wrong unit, because it makes a difference. If you don't speak the right, it's all about speaking the right language here. I don't even know what. If Q represents something in physics, I don't know what it is. Probably does somewhere. We use all the letters. All right. Leave that a couple more seconds in the off chance anyone's copying that down. Yeah.
On the tests, are you picky about significant figures?
No, that's a great question. So, beautiful thing about physics, no one ever told me this for some reason, but so in chemistry, you have that whole significant figures, and they have a whole list of rules for how to do that. One of the interesting things with physics is it's just kind of this rule of thumb that no one really says, but 2 or 3 decimal places is kind of what people do. 2 or 3 decimal places is good by me. So whatever your answer is, decimal followed by 2 or 3 numbers, great. You don't want to round too much, but 2 or 3 decimal places seems to be what most physics instructors are happy with for whatever reason. I don't know who decided it, but it just seems to be what everyone does. So that's what we'll do as well. I like it. It's the right amount of detail without too much work. All right, so it's important to talk about insulators and conductors. Real straightforward, but long story short, insulators do not conduct. electrons in charge, they're stuck. So we have our atoms here. You have your protons and neutrons in the middle, you have your electrons, and they're stuck there. And the reason that's significant is in a conductor, those electric clouds overlap each other. And the electrons can zip around and move around. We're going to talk about current and electricity eventually. But for now, the important thing to talk about is that if I have an insulator and I put some extra electrons here, they're going to stay there. They can wiggle around a little bit. There's a little bit of wiggle room. They can spread out a tiny bit, but they're largely stuck. Whereas if I put some extra electrons on here, it's going to spread out among the whole thing. It's going to spread out as much as possible. They're going to cover as much of the surface as possible. Spread out. We're going to learn that rule in a little bit. That whole opposites attract and like charges repel. But that's kind of the big thing to point out there. So they can flow freely. And so when I bring, for example, this is a good time to introduce this idea. Real straightforward, it showed up in this picture. I believe I cover it later, but 100% do, but it's good to point it out now. Rule of thumb, I think it's going to show up, I'm 100% sure it's going to show up later. Opposites attract, like charges repel. So I'm going to jot it down now, just to make certain, because the more I repeat it, the better it is. Opposites attract, like charges repel. This is something that's different about charges and gravity. There's lots of things that are different, but this is one big one. Gravity always attracts. Two planets always go towards each other. You're never going to find planets pushing away from each other. There's no such thing as negative mass. But with charges, you have positives and negatives. So if I have two positives, they're alike. They repel. If I have two negatives, they're like. They repel. Positive negatives attract. So with that in mind, if we look at our beautiful picture here, we have this positive rod. How do we charge it up? Rubbed up against something. Solely electrons. We're going to learn that electrons are the only things that can move. And so you bring here a piece of metal, and on this metal, it's going to push away the positive charges. I'm doing air quotes here because we're going to learn that protons you can't move. Protons are in the nucleus of an atom. So if you move the protons, that means you're moving the atom. And so if you just think in practice what that would look like, that would mean if I move this positive rod near this metal, the metal would physically deform and all the atoms would push to one side, which obviously does not happen. I've never seen someone bring a piece of metal near something and the thing physically deform and bend away. At least nothing sizable. What will happen is the electrons will pull towards that side because the opposites attract. They'll pull on towards it. All the electrons will stack up over here. Before, they were all over the place. This piece of metal started out with electrons and protons evenly spread out. All was well in the world. They brought this positive rod and it ruined everything, and all the electrons zipped their way on over to the left side. And we're going to find in this class that if you get rid of electrons, if I move these electrons over, oh look, now I've got extra positives on that side. So positive is merely the absence of negative. Maybe there's a philosophical statement you can take out of that. I don't recommend it. But in this case, that is the reality. So whenever we talk about something having excess positive, that means it lost its negative electrons. I'm going to mention that a bunch of times as well. It's going to show up later more explicitly in the writing, but again, the more I can mention these important facts, the better. So there you go. And dipole. So if I bring this near an insulator, I told you they could wiggle around a little bit. Here's the idea. If I bring a positive charge over, and these are just kind of concepts, they're not necessarily going to show up in the problems, but it's important to talk about. If I bring a positive charge over, it's going to actually pull the electron cloud a little closer to it. It's not going to rip the electrons free, unless it's really strong, but in this case it's not. It's going to kind of pull them off to the side, and so you get an area that's a little bit more negative, you get an area that's a little bit more positive. We call this a dipole. Di stands for two, pole stands for poles. I don't know, not too much more to say there. So this thing ultimately gets a positive end and a negative end. I have two poles of this thing. Why a hydrogen molecule has a dipole to it. It's a little bit, they call them a little bit different, they call them hydrogen. Dipole just because it's stronger than other ones, but you can wiggle around this electron cloud, so even insulators you can charge a bit. Again, I'll bring a balloon next class or something, and you can do this for all sorts of fun little things. Stick a balloon to a wall, all that kind of stuff. It works this way. All right. So, it's a good question. If I make this dipole, and remember that rule, opposites attract. So just think about this one. There's no math to do here. I bring a positive charge and a negative charge to your insulator. And the question is, what is the direction of the force? Is it going to push, so then in this case it's pulled, and A it's pulled towards the positive and it's pushed away from the negative. And B, it's pulled towards the positive and pulled towards the negative. C, it's pushed away from the positive, pushed away from the negative. And D, it's pushed away from the positive and pulled towards the negative. Think about it for a second. I'll give you the answer. But just think, what do you think would happen based on kind of the pictures that we've seen so far? Let's draw some pictures. So there's no math to be done here. No math to be done, just conceptually. So let's explore what's going to happen here and give myself some space to draw some beautiful pictures. So we bring our positive charge over. Use 3 colors. Red will be positive, blue will be negative, black will be the box. So there's my positive, there's my negative. Remember, all objects are made of protons and electrons. So both of these insulators, they have some protons. And let's be color-coded here. They have some protons in them. They're evenly distributed. We'll assume that, make our life a little easier. Because it should be, unless there's a hole in the object. And they have some negatives. And they're all just chilling there. Boop, boop, boop. There we go. Beautiful, right? All right. This positive charge, I bring it near the insulator. Remember, an insulator, they can't move all the way. They can't freely move. It's not a conductor, but they can move a little bit. And remember that mantra, opposites attract, like charges repel. So when I bring this positive over, remember the electrons are the only thing that can move. The protons can't move. They're stuck to the nucleus. If they move, then the whole object is moving. So the protons can't move. Only these electrons can move. Which way are these electrons going to move to? Left or right? Left. Pretty straightforward. These electrons are going to give a little shimmy, move on over, move a little bit closer. Oh goodness, that's so many things to do. So they're going to shimmy on over. They're going to bump their way onto the left side. Shift over just a little bit. Not a lot. Not a lot. They can't move that much. It's an insulator, but they can move a little bit. Boop, boop, boop. And so now when we look at this, all the negative charge are just a little bit closer. So what we can ultimately do is approximate this big box up there. Oh, I need more room. Goodbye, bottom problem. We hardly knew you. All right. We can approximate this problem as we have effectively made a giant dipole. We've effectively moved all the negative charges over a little bit, and the positives are just a little bit shifted to the right. You know what? Let's move them a little closer to make it, just to show how small we've moved them. Not very much, but we can average it like that. All right, and we are going to learn in this class that just like gravity, the closer charges are, the stronger the force. So this negative one is now closer than this positive one is. These two positives will certainly repel. In fact, let's draw that on here. These things will certainly repel, and they're going to repel, if you all remember from Newton's third law, that's going to show up again in our slide, equal and opposite. Whatever happens to one must happen to the other. So they're going to repel, but the negatives are going to pull just a little bit stronger because they're closer. So ultimately, at the end of the day, what's going to happen? It's going to attract. So if I have this positive charge and I bring it near it, ultimately it will attract to it. And I can repeat this whole problem. And I can just flip everything. Change all these reds to blues. Change this to a negative. And then all these electrons get pushed a little bit to the right. Leaving me with kind of the opposite situation. Well, opposites in some ways, same in the others. Move this bad boy on over. Draw the other one real quick. So I'm not going to spend the time to draw this beautiful picture as I did the first time. But the long story short is that the negatives would push slightly more to the right. The positives would be slightly closer, and we have the same situation. The positives, because they're closer, are going to pull stronger. If you look at my arrows, they are purposefully sized, that the red arrow is a little bit closer. So long story short, they will also pull towards it. And this explains why when you've ever played with balloons and you rubbed it on your hair and you built up charge, it stuck to stuff. Why? It stuck to the wall. If you ever did this in your physics class in high school, if not, sorry, you missed out. But if you've ever played with charges, if you've ever done laundry and your clothes are all stuck together, this is why. It's because when you have some extra charge and bring it near something, it's going to end up pushing the opposites away. The ones that are closer will stick to it. So charge up a balloon, it'll stick to your hair, it'll stick to the wall. If you have a little stream of water going, it'll pull the little stream of water over, it'll pull up. It always will pull on it. So just an interesting thing there, and now you kind of know why. Positives and negatives attract. The closer they are, the stronger that is. All right, so speaking of that force, what is that force? Well, I mentioned the guy Coulomb. That's the guy where the name charge came from. Coulomb came up with something called Coulomb's law. And this is an important time. This is a great time to remind you all the difference between laws and theories. Laws are an observation of reality. Example, gravity. This pin will always fall towards the earth. That is a law. The law of gravity is that two objects of mass will always pull towards each other. Why? It's a great question. That's where theories come in. Laws are kind of set. You can't really disprove them because it's just a description of reality. If you disprove them, then you're saying that our perception of reality is like things with mass aren't pulling towards each other, which that'd be a hard argument to make. Maybe something in the universe is like that, but Coulomb's law, it's kind of like gravity but for charges. Coulomb's law says if I have a positive and a negative, they're going to attract towards each other. Positive, positive, are going to repel. Negative, negative, they're going to repel. And he actually calculated what they are. So Coulomb, there we go. This is just fun facts. We'll learn about amperes eventually, but it's based. Hey, look at this. Nice little fancy. So the amperes for current, we'll get to it eventually. It's a little preview. There's a reason why these units are named what they are. There's a reason why 1 Coulomb is what it is, and it's defined based on measurements of specific things. A Coulomb, 1 Coulomb, is defined as the amount of charge that generates a force of 2 dynes per centimeter of length between 2 wires 1 centimeter apart. All you need to take away from that, you don't need to know that. Just that one Coulomb is the amount moved by 1 second, and it comes from the definition ampere. All the units, their definitions come from experiments. It's a whole fun thing to investigate. Why is a kilogram a kilogram? Why is a meter? Why that set amount? Great YouTube videos. Look it up. Highly recommend it. But here's Coulomb's law. Here's the punchline. The force of one charge and another charge is the following. K, which is a constant. It's a beautiful constant. It's so nice. 9 times 10 to the 9. Just rolls off the tongue. 9 times 10 to the 9. Take charge 1, so you have 2 charges, multiply by charge 2, divided by the distance across it, and I do not know why this 2 is on the bottom, but that was some bad, it's a little typo, good thing I caught that, divided by the distance squared. That 2 was in the wrong spot. So, if you ever have the numbers in the bottom, it's an adjective. This is charge 1, charge 2. This is the force of charge 1 on charge 2. If you have the numbers up top, then it's squared or cubed or whatever it may be. In this case, squared. So, it's a law because if you have 2 charges, this is how you calculate the force on it. Just is what it is. You get something that measures force, and you get 2 known charges, and you set it a certain distance, it will always give you this force. This does not explain why they push away from each other. This just says how much they do. It just says how much they push away from each other. And notice this nice little arrowy thing up here. That denotes that force is a vector. So in this case, force is a vector based upon where they're oriented. We're going to see some problems with that. It is a vector. It has an amount and it has a direction. The unit here is newtons. And don't forget the squared. You are going to hear me repeating a lot of times. Hey, I tell my students this in class. The reason I repeat that stuff is because humans tend to make the same mistakes. If I teach the same class 5 different times, humans on average act in certain ways. Individually, we're very unique. But as an average, we tend to do the same kind of things for whatever reason. Whether you like it or not, it tends to be a trend. Look at history. There's a lot of repetition there. So towards that end, I tell my students, if you make a mistake when solving this problem, this is about half the time why you made that mistake. You forgot to square the distance on the bottom. You forgot to square, when you plugged in the distance here, you forgot to square it. It's just a classic. People see that squared, they'll go all the steps, they'll write them right. Step 1, they'll write the givens perfect. Step 2, they'll find the, hey, I'm trying to find force. Step 3, they'll write the equation correctly, and then they plug in the numbers and they forget the squared, and it's really sad. This is really important, especially when you have a multiple choice problem. I will give quiz problems where 2 of the answers, the only difference in the calculation was one of them was squared, the distance was squared on the bottom, and the other wasn't. So, you may get the right answer. You'd be like, I got one of the answers there. Yeah, I kind of did that on purpose to see whether or not you squared the bottom or not. So be careful. And as I mentioned, opposites attract. There it is. In all its bold uppercase glory, opposites attract like charges repel. This is the law because this is just what charges do. Just an observation. Does not explain why. Theories explain why or do their best to do that. Theories can be wrong. If we just prove it, laws are pretty set in stone because it's just an observation. It just says they do this. They push away from each other. Here's how much they push away. That's it. So it's taken me a long time to understand the difference between laws and theories, but it's a really interesting one at that. So we got 4 minutes left in class, Joe. I'll quickly just show you some pictures, and then we'll leave some problems basically for next class. We've made pretty darn good progress. So because we made pretty good progress, next class is going to be a good amount of problem solving. I'm going to do some longer ones, but let me leave you all with this picture, and then we'll call it good. You have 2 charges. They repel. Here's the distance. Again, it's just another way of seeing, like, it's the same exact thing as covered, just a visualization of it. And you can see here, we have vectors. They point away, they point towards each other. I'll stick around for a few minutes, y'all. I know I'm finishing 3 minutes early, but I don't want to start a problem with 3 minutes left just because there's not enough time to do it. I don't want you to be hanging on that. But good opportunity. If you have some questions, you want to come up and ask me. I will step down from, I will stay up here only so that you have a bit more privacy. If I move down there, maybe closer to people if you have something private you want to tell me. So I'll only stay in my high seat up here. Feel free to walk on around, join me. The view is great. If you have any questions coming up, ask me. That way we can have some privacy. Great first class, y'all. No. You all do not have discussion this week. Next week is the beginning of discussion. Yes, sir.
It's just a discussion, no lab section?
Yes.
Okay.
There is a lab, but it is not with the course. It is a separate thing.
It's not required?
It is required.
Okay.
Double check your, I don't know,
I'm not 100% sure because I didn't go writing in this course because I took physics 1 with calculus.
Oh, yeah.
So, like, I'm kind of not sure.
Double check your, graduation card. I'm pretty sure it is required, but you do not have to take it at the same time. You can take it literally anytime.
Okay, I'll check.
They made it interesting though. They made it hopefully more useful. I don't know how your physics 1 lab was. Was it web assigned and all that stuff?
It was back during COVID, so yeah.
Oh, yeah. So they made them, in my opinion, they're different now. They're completely separate.
Alright, thank you.
Yeah, what's that?
So I have 2 questions.
Sure.
Kind of like follow up. So whenever you're like doing a presentation, do you ever upload like your PowerPoints with your drawing notes
I
on?
will do that literally after this class.
Okay, awesome.
And it will be titled the name of today's date, and then the slide.
I just didn't know if you did that or like you just left up the YouTube like live
No,
stream
I would do
or- Oh, okay. Perfect.
Speaking of which, in the live stream, thanks for reminding me.
Oh, the live stream's going.
Yeah, it should still be going.
I didn't know it was-
Everyone's going to know you asked that question now.
Oh, okay. That makes sense. I used to.
Yeah. All right.
Alright, yeah.
Yeah, okay.